Uh, cool then, guys. So the agenda of this meeting is pretty straightforward. To okay, actually, here's my name. Fine. Anyways, let's start. So the agenda is pretty straightforward. This is book reading for DDIA, and today we'll be discussing the first chapter. I've already shared the PDF with you guys on the WhatsApp group. You can open that, and I'll share my screen, and then we can just go through the chapter step by step. Right? Uh, like, am I audible clearly, or is it low from my end?
You are audible.
Yeah, you have.
Okay. Okay. Good. Anyways, I'll try to speak a little bit aloud. Uh, Fine. Let me share my screen then. Discuss the chapter. Hmm. Share. Yeah, if you guys are okay, we can also shift it to Meet actually later on. Hey Sarang, hello. You guys can see my screen, right?
Yeah, it's visible.
Okay, fine. I think let's start with the chapter then. Let me see whether there's a presentation mode for it. I actually use this one a little less. Or what I can do is let me just stop sharing and open the PDF in something else. Not a fan of Adobe. Hey guys, so yeah, for Nishant and Sarang, we are going to discuss DDI right now, and again, it's pretty straightforward to be really honest. Initially, I'll not require you guys to have any pre-reads. Later on, I will ask you guys to read a little bit so that it becomes easier for me and for everyone else as well. Yeah, I think I have a better tool to display the PDF now. Share screen, share screen. My monitor laptop will be too small. Oh, sorry, monitor will be too small. You guys can see my screen?
Yeah, it's visible.
Yeah,
Okay,
we can.
okay guys. So this book is mainly related to system design, and how to design any sort of applications. So earlier, like in the starting, we'll just go ahead with two books. One is DDI and one is for ML, which we can discuss. And then post that, then there are certain specifications. And if you're a backend guy, I'll recommend those books to you guys. And if you're, let's say, an ML guy, I'll recommend those books. I've myself gone through these books, so I know that they're good. So yeah, maybe let's start. So I think the first chapter is related to reliable, scalable, and maintainable applications, right? Whenever, let's say, you try to design an application, they're related to three things, which is reliability, scalability, and maintainability. If you guys can see here, the first thing which the book mentions is that many applications today are data intensive, right, as opposed to compute intensive. And raw CPU power is rarely a limiting factor. I mean, this book was written when there were no LLMs. So that is why this line is actually kind of contradicting right now, because raw CPU power is kind of a limiting factor sometimes, and we tend to use GPUs now because of LLMs, right? But in any of the other backend applications, it's just the data intensive part which is actually tough, and CPU power is not a limiting factor, right? When we say data intensive application, it will obviously require things like databases, caches, search indexes, batch processing, and stream processing, right? When I say all of these things, I'm pretty sure you guys are aware of databases, caches. Search indexes are, let's say, for searching, you try to create index, right? What is an index? So let's say if I actually had to search from 1 to 100, right? So one way to do it is to either do a linear search. Another way to do it is either do a binary search, right? But if I let's say have bucketed my 100 into buckets of 10, right, and then I try to search 20, I just directly need to go to the second bucket and then I need to do a linear search, right? That is how indexing works basically. Worst case, let's say if you try to create the maximum number of buckets, then you might not be optimal. And if you try to create less buckets, you are as good as linear search, right? So the complexity in indexing actually lies in deciding the number of buckets in which you want to index into, right? So that is a little bit about search indices. Like, I don't want to go into extreme detail because that will come forward. Then there's another thing called stream processing. Again, send a message to another process to be handled asynchronously. We use messaging queues for this, right? And the last thing can be batch processing, right, which is analytical data. So I think there are two separate branches like OLAP and OLTP, and one is analytical and one is transactional, right? Transaction processing is basically like when you have a lot of orders coming, right? Those are like transactions. And when, let's say, if you have any analytics, let's say telemetry or any atom stats is a very good example of it. That can be analytical because it's a pipeline which is going to run over a day. Right. And again, the book mentions if that sounds painfully obvious, that's just because the data systems are such a successful abstraction that we don't end up thinking about too much, right? What this basically means is that you actually don't end up thinking, okay, I'm using Postgres, I'm using all of these SQL DBs, how are they actually internally implemented? We do not need to think about all of that, right? So, like, is this part clear to you guys?
Yeah.
Yes.
Yeah.
Cool. Okay. But again, as it mentions, that reality is not that simple. There are many DB systems with different characteristics, different applications, different requirements, right? There are various approaches to caching, indexing. A lot of things are done, and there's no one correct way to deal with things. And the book will basically help us decide, okay, what are the correct ways, and how can we use them in concatenation? When do I use a cache? When do I use this? And the worst part about all of this is deciding, let's say, the right kind of cache to use or the right kind of DB to use. That it's blurred, right? It is blurred because there's no hard and fast boundary. Redis is used as a cache. So if we go here, right, thinking about data systems, we typically think of DBQ's cache as being very different categories of tools, right? But they're actually not. Why? Because they have like DB and message queues have some superficial similarity because they store data technically, right? But they're separate access patterns. A message queue might not require the data to be persisted, right? But while a database usually does require the data to be persisted, right? That is just one example where it can be different. But there are a lot of separate tools. Let's say Redis, right? There are data stores that is user messages queue. So Redis was actually a DB, which we actually end up using as a messaging queue, right? And then there are message queues like Kafka, and like almost all of big tech, they would love to store all of their data, all of their analytical data into Kafka, right? They persisted there. All of your big data is persisted most of the times in Kafka. So again, so it's not like a messaging queue can be only used like a messaging queue, and it's not like a DB can be only used like a DB, right? It depends on your user, and sometimes, let's say, a DB might be a better fit for a messaging queue, or vice versa. Again, secondly, increasingly many applications now have such demanding or wide-ranging requirements that a single tool can no longer meet all of its data, right? Even in our company, if you see, we're trying to check for Arctic or Postgres, then we also use RabbitMQ. We use a bunch of separate tools, and the tough part is how do we stitch them together? Again, you have an example here that if you have an application managed caching layer, right? What does this mean? Application managed caching layer? It means basically it is a software caching layer, right? What do you mean by software caching layer? So a thing which is not separate from your code. In your code only, you're trying to, let's say, save things into a list. That can be a memcache thing. Or let's say if you're familiar with Android or iOS, there's something called shared preferences. They can be application managed caching layer. Or let's say in your backend, uh, again, you might store your data in a front end. A front end is a very good example, right? In front end, you might end up caching all of your data into the front end itself, right? Into a Redux state or something. That can again be application managed caching layer, right? Or you can have a full text search server. What does this mean now? Full text search server means that, okay, sometimes you can actually do searching while being in SQL, right? And then you can, let's say, implement the search logic by implementing a library. So let's say there is a library called Lucene. Apache Lucene is a very famous library. And that library, what it does is it will help you implement searching algorithms internally in the app code, right? But then you need to have indexes in your database. But my database does not require to have all these indexes. Why? Because my database, let's say, will have a lot of data. It might have a data for users. My tables can be used for multiple things. And to power my search, I do not want to update my main database, right? Because that is a very expensive operation. So what I do is I try to create another DB called Elasticsearch, where indexing is done separately, so that I don't affect my actual DB. And every single time I need to search, I don't let's say increase the compute cost of my DB. Right? I can directly go to Elasticsearch, which is separate from my main DB. So these are again examples where how you can cache. And again, it mentions one of the ways where you can basically use application code as cache. And you can, if you can see here, you have an application code, right? Your application code has a cache itself, in memory cache. If the cache misses, it'll go to the database and then it'll capture changes to data. And then my application code will again update my cache, right? It's pretty straightforward. I'm not going into detail because again, this will come later in detail. This is just to tell you that, okay, your cache can be either a completely separate thing or it can be managed through software. Is this part clear to you guys?
Yeah.
Okay, fine. Then is when you combine several tools in order to provide a service, the services interface or API usually hides those implementation details from clients, right? I think we all of us are aware of APIs. Whenever you expose an API, you're not exposing anything else to the client, right? You're just exposing the API. That's a great thing about APIs. Your composite data system may provide certain guarantees that the cache will be correctly invalidated or updated. So it is just talking about reliability, right? And it is just telling you that, okay, now you're not just an application developer, but you're also a data system designer because you were able to think about when to use a cache, what kind of cache to use, and when to use a message queue, and when to, let's say, have a full-fledged search engine. Again, very high level, very, very high level. We'll go into extreme detail of all of this, right? There are many factors that may influence the design of a data system, including the skills and experience of the people involved, legacy system dependencies, the time scale for delivery, your organization's tolerance of different kinds of risks, right? Basically, while designing a system, you need to take care of a lot of things, the money you have, the kind of risk you can take, the kind of availability you want. All of those things are mentioned here. Sorry. Okay. In the book, like the main thing is to focus on three things: reliability, scalability, maintainability. I will go into each of them, but reliability means whether a system is reliable or not. When you say anything is reliable, it can be reliable in multiple terms, right? It can be reliable in terms of functionality, whether the user is able to do whatever is required. It can be reliable in terms of safety, right? That my data is not going to get lost or going to misused, right? It can be reliable in terms of fault tolerance, right? That it will be able to withstand, let's say, user errors and all of those things. Whenever you guys have any certain doubt in any of the words which I say, please ask. Then and there, it gets easier. And then comes scalability. Scalability again, when you grow, your system grows. Simple. Maintainability, which you guys again do, right? Let's say some X guy wrote the code, and then you're like, I don't understand what the X guy wrote, right? And we tend to say that I was not there when this code was written, right? So we need to write it in a way so that the next dev is able to understand it in a good way. And let's talk about reliability now. Again, intuitive idea everybody has. Application performs the function that the user expected. It can tolerate the user making mistakes or using the software in unexpected ways. I will elaborate on this again. Its performance is good enough for the required use case. Yeah, that is something which I missed, right? So like my performance should also be good enough. It's not should not be like the screen is constantly loading, right? What's the point? If we are, then we are a government banking website. Uh, yeah, the last thing is the system prevents any unauthorized access and abuse. The same security issue. If all those things together mean working correctly, then we can understand reliability as meaning roughly continuing to work correctly even when things go wrong, right? So this is what you can understand uh, a rough meaning of reliability, right? continuing to work correctly even when things go wrong. When things that can go wrong are faults, and systems that anticipate faults and can cope with them are fault tolerant or resilient, right? The term fault tolerant is actually like a misnomer. Why? Because it actually suggests that we can make a system tolerant of every possible kind of fault, right? Which obviously is not possible. Again, there's an entire planet Earth analogy, not a fuse. Sorry. Yeah. Note that a fault is not the same as a failure, right? So a lot of times when we say words, we sometimes actually do not think about them, right? A fault is a simple fault. A failure is your, let's say, site is not accessible. That is a failure, right? A fault is a simple bug. Let's say you are getting a notification twice, can be a fault. A fault is usually defined as one component of the system deviating from a spec, where a failure is when the system as a whole stops providing the required service to the user. It is impossible to reduce the probability of fault to zero. Obviously, we constantly have infinite bugs in our system, right? Therefore, it is usually best to design fault tolerance mechanisms that prevent faults from causing failures. Uh, Counterintuitively, in such fault tolerant systems, it can make sense to increase the rate of faults by triggering them deliberately, right? So what does this actually mean is it is talking about testing actually, right? So how do you do testing in huge production environments? You use something called a chaos testing mechanism, right? What does chaos testing do? Okay. So if you guys have, let's say, seen Three Idiots or any other movie, right? So how do they check whether the entire system was working? They will try to, let's switch off everything and then try to see that, okay, is this going to work? Is this going to work? Is this going to work? You're going to try every combination of, let's say, switch on and switch off to try to see whether the inverter starts. Right? Same thing is here in Chaos Monkey. So let's say if you have 5 services, I want to see that, okay, if my X service is down, will my major feature still be provided to the user or not? And to do all of that switch on, switch off, you use something called Chaos Monkey. Chaos Monkey is a software which is built by Netflix to do chaos testing. Uh, and again, it is just mentioning, but like that is the best way to actually check it, right? By introducing the faults themselves. Another thing is that this is a very important thing, that although we generally prefer tolerating faults over preventing faults, there are cases where prevention is better than cure. Okay, what does this line mean? Can anybody explain this line to me? Prefer tolerating faults over preventing faults.
Basically, it's hard to prevent like all the failures, all the edge cases. Rather than we can do some alternatives so that we can face that edge cases and try to improve the code over there, rather than like ignoring or like try to handle all each edge cases.
Exactly, right? Perfect way in which Sandeep described. So let's a very common example of this is, let's say, your search engine, right? Even if you, let's say, mistype something, you still get search results, right? And what that search results might show is an incorrect result, right? Let's say I was typing Sandeep, right? And instead of double E, I press double three for some reason, because E and 3 are very proximal on the keyboard. So I just typed that, and it might end up searching something with 33 in it, right? So it might end up showing you a wrong result, which is okay to have. But if I don't get to see any result, then it is basically preventing fault, right? I just don't allow the user to type 33 in a search box where only text is required, right? That is one way to prevent faults. But obviously, a lot of times you end up not typing correctly, right? And you still want the search results to be seen. If the user is not able to see their wanted search result, they might again type. You assume that the user is smart enough to reuse in a correct way, and that is a way in which you are basically tolerating a fault instead of preventing a fault. Right? Preventing a fault will be just not showing any search result to the user and asking user that, hey, you made an error. Please type again. That is not what happens with any of the modern search engines. So that is one way to tolerate faults. Again, but there are certain places where you do not want to tolerate faults, right? You want to prevent them. The best way is username password, right? You don't allow the user to enter the wrong password, right? Even if it is missing by one character, it is wrong. And that is a place where you would actually prevent faults instead of tolerating them. Yeah, this is what it mentions in English. Yeah. So now there are other faults, which are hardware faults, right? So what your hardware faults are, they're pretty simple. When does your hard disk fail, right? We have all used certain hard disks. After, let's say, 5 to 10 years, you will realize that okay, it might be slowing down, or it might not be the best one, or sometimes it crashes completely, right? So hard disks have actually a mean time to failure of about 10 to 50 years. Mean time to failure is like average time it takes for a hard disk to fail. And when I mention hard disk, I actually do not mean this one hard disk. I actually mean a storage cluster with 10,000 disks, and which means that we are expected on average for one disk to die per day, right? Which is a fun fact if you think about it. That on average, one of your disk will die, and that is why to let's say tackle this, we go for RAID, right? Which is redundancy, nothing but redundancy. I don't know the full form right now. I am forgetting it, right? But it is nothing but redundancy. RAID 0, RAID 1, RAID 2, RAID 3, right? RAID 0 is that you have zero backup disks. So whenever this one disk fails, my function will stop, right? I have RAID 1 is this one, RAID 2 is two copies, RAID 3 is three copies. It's nothing but copies, right? So it is saying that disk may be set up in a RAID configuration. Servers may have dual power supplies. If a power goes, you need one inverter, one generator, one some other power source, one solar, right? And hot swappable CPUs, right, where the cores are engaged. So basically, there are a lot of separate backups which you can keep to avoid hardware faults. That is what I'm talking about. And again, when one component dies, the redundant component can take its place when the broken component is replaced. Again, this cannot completely prevent hardware problems, and it is well understood, right? But actually, what you guys will realize is that hardware faults is the thing which only causes 10 to 25% of outages. I'm skipping ahead, but I just wanted to show you this stat that hardware faults played a role in only 10 to 25% of outages. The major thing is human error still, right? Even after ChatGPT, we're not there. Uh, so again, going back to hardware faults, until recently, redundancy of hardware components was sufficient for most applications, right? Redundancy is most of the times more than enough, right? But redundancy of components, not the machine. As long as you can restore a backup onto a new machine fairly quickly, the downtime in case of failure is not catastrophic, right? As soon as you can just basically do backup, it is good enough. Thus, multi-machine redundancy was only required by a small number of applications. Let's say bank servers are a very good example for somebody deducting account, right? If my main machine dies, I would still want it to be reflected on some machine out there, right? Otherwise, a wire transfer will be launched and there'll be like a fraud for money. So there, multi-machine redundancy will be required instead of multi-component. Multi-component is again, to reiterate, component redundancy is like you have RAID 0, RAID 1. Multi-machine is you have multiple clusters themselves. Again, so however, as data volumes and applications computing demands have increased, more applications have begun using a larger number of machines. Again, we use AWS, and it is fairly common for VMs to become unavailable without warning. Why? Because the platforms are designed to prioritize flexibility and elasticity over single machine reliability. Uh, Everything clear till now?
Yeah,
Yeah.
it's clear.
Like, do let me know if I'm going fast or slow, or if I'm missing something. Just please tell me that, okay? Okay. uh, Fine. Hence, there is a move towards systems that can tolerate the loss of entire machines by using software tolerance techniques in preference, right? In preference or in addition to hardware redundancy, right? A very good example of this can be, let's say, your local cache, right? Even if your main cache or if your main DB is lost, I still have a local cache on the front end which will be able to, let's say, uh, make the things work at least for some time. Let's say I have my Facebook infinity scroll or some homepage of, let's say, Twitter, right? I can cache things on my browser so that the user is still able to at least see the tweets which are cached there, right? And if I don't have that, then like even if my DB fails, my all of the other things will fail if I don't have a local cache. So that is what it is trying to say, that okay, if you have a hardware fault, you can still have a software fault, still have a software mechanism to solve it. Now let's talk about software errors. Again, We think of hardware faults as being random and independent. Obviously, if light goes, it goes, right? You can't do anything. If there's a natural disaster, like it's raining right now, your like data center might be affected. You can't do anything there, right? There are weak correlations. What does this mean is that, let's say your hard disk is in one cluster, right? If the entire data center gets fire, everything will be uh, like gone, right? So there is a weak correlation. But other than that, it is nothing else. So another class of fault is a systematic error within the system, right? These are harder to anticipate because they are correlated across nodes. One good way to say is that, let's say my order in strategy engine was of a wrong template, right? Then what happened was that all of my other things in OMS failed. Then everything in analytics was starting to get reflected in a bad way, right? And that way, it is a cascading fault, right? Everything else succeeding the fault is going to make everything fail. So that is what a systematic error is, right? A software bug that causes every instance of an application to crash when given a particular bad input. Uh, for example, consider the leap second. So there is a concept of leap seconds. Again, if you guys are into atomic clocks, you can read it up. Consider the leap second on June 30. This caused many applications to hang simultaneously due to a bug in Linux kernel. You can't anticipate that, right? Until you actually face a leap second. Another thing is called a runway process, right? What a runway process is, it is a process which basically is in an infinite loop and it creates another process. You know? So what ends up happening is it ends up creating too many empty processes infinitely, and then it ends up filling something called the proc table, PROC table, right? And that proc table is what basically allows you to run any other program. So unless you clean that program and all of these processes associated with it, you will never be able to use anything. So that is what a runway process is. And that can again cause faults, right? Another thing can be a memory leak somewhere. Again, here same thing, cascading faults. Is there nothing there, right? There's no quick solution to the problem of systematic faults in software. Lots of small things can help. Carefully thinking about the assumptions and interactions in the system. Thorough testing, process isolation, allowing processes to crash and restart, measuring, monitoring, all of those, good old classic ways of CS are the ways you solve them. If a system is expected to provide some guarantee, for example, in a message queue, that the number of incoming messages equals the number of outgoing messages, right? A very simple check which you can put in a messaging queue, right? And it can constantly check itself while it is running and raise an alert if a discrepancy is found. That is how you make alerts, right? That is how any system will be able to say that my message failed, right? It is constantly tracking incoming is not equal to outgoing. Now let's talk about the toughest errors to solve, human errors, right? Human errors are the major ones. Very good example of this is if you guys would have seen that Facebook crashed, I think, some time back because of some errors in DNS resolution, right? They put some wrong entries in the DNS server, domain namespace server, and then basically everything, my sites were not getting directed to my actual instances, right? If I, let's say, enter sharksigma.com, I might not reach the instance on which it is deployed, and all of that is done through DNS. So biggest human error ends up happening too many times. In fact, one study of large internet services found that configuration errors by operators were the leading causing out of outages. Most of the time, it's network error. Like say companies like VMware and Nutanix, all of these companies tend to do these errors. So how do you solve them, right? You design systems that minimizes opportunity. Again, you make abstractions so that operators can use it easily. You decouple places, right? So basically, you so that you don't have a single point of failure, you break it into multiple pieces. Another thing is sandbox environments, right? Where basically you provide them a staging environment so that they can test it in a environment which is very close to production, right? It is not a local, it is not a production, it is an environment which is mimicking production without any user. Another thing is that testing, right? Which I think Sarang keeps on focusing. Automated testing, automation testing, manual testing, integration testing, chaos testing are ways in which you eliminate human errors. Allow quick and easy recovery from human errors to minimize the impact in case of failure, right? Basically, it is talking about rollback. The rollback is, let's talk about AWS, right? you can easily roll back your deployment on EC2, right? It's very easy. You can just click on rollback, it rolls back. Otherwise, what you would have done, let's say if you did not have the capability to roll back, you would try to override everything. You will delete all the files which you had implemented, and then you will redeploy all the files which were in your previous commit, right? But with the rollback thing, it becomes very easy. How does rollback work? How does rollback work is actually pretty straightforward. It will try to maintain it in a Git system where it will try to maintain separate images of your commits, and it will try to deploy them. Again, can go in detail, but first chapter, let's keep it light and busy. Again, another way to reduce human errors is telemetry, right? Logging, basically. If you are able to log, if you can see that, okay, if my pipeline runs, I see info logs of about 100 and error logs of 2 because of, let's say, network errors. But if I get error logs of 500, I clearly know that something is wrong, right? And telemetry is one way to do it. Telemetry is nothing but logging. Now let's talk about how important is reliability, right? It depends where are you using it, but it is not like reliability is something which you can take for granted, right? It is not just for nuclear power stations. It is expected to make any of the applications you work in a great way. A very good example of this is Google Photos, right? If everything is lost there, so even in non-critical applications, if the pictures are gone, then it is actually a bad user experience, right? We should be reliable there. Now comes scalability, but even before going there, there's this line, right? There are situations in which we may choose to sacrifice reliability in order to reduce development cost. When developing a prototype product for an unproven market, like us, right? We can actually sacrifice reliability so that we move forward. A lot of times, let's say, even if our feature is not complete, we want to make it reliable. How? First thing which you want to achieve is that our order should be completely processed, right? That is why, if you would have seen, Sarang was constantly focusing on us to complete the order management flow so that we are able to place our order, because that is the first basic thing which we require. All the other things we can manage later on, right? And because we don't have any user, we can sacrifice reliability. We can, let's say, put a service down. A very great example, right? You can just simply switch off things right now because there's nobody using it. So that is places where you will sacrifice reliability. And again, there are multiple other places, and those will be discussed in the book in detail. Right now, it's the first thing, so I will not go into much detail here. Okay, after reliability comes scalability. Scalability, again, system is working reliably doesn't mean it will necessarily work reliably in future. Constant struggle. If it is working for 10 people, it might not work for 10,000 people, right? Simple. When I say scalability, it does not mean that X is scalable and Y does not scale, right? It is not a label. You cannot say that in where it is scalable, how it is scalable, whether it is scalable in terms of reads, whether it is scalable in terms of writes, right? And to define all of that, you need to basically tell what is the load, right? Unless you know the load on the system, you won't be able to define the scalability of the system. So let's try to define the load on the system. Load can be described with a few numbers called load parameters. Obviously, you need to quantify load. A very good way is that you see requests per second, right? How many requests you'll be hitting. That is the first thing you see in a server cost. Another thing in databases is the ratio of reads to write. One thing can be the number of users. One thing can be hit rate on cache. These are ways you basically check the load of any system. Again, average cases. Perhaps the average case is what matters for you, or perhaps a bottleneck is dominated by a small number of extreme cases, right? Most of the times we'll try to solve for average cases, but let's say you have a huge sale coming up, right? You know it is going to come up, so then you only scale up and then you again scale down. Again, I think they have described the example of Twitter here. And so, okay, this is a good case study for all of you guys. So let's say you have Twitter, and there are two main operations for Twitter, right? One thing is posting a tweet. A user can publish a new message to their followers. 4.6K requests per second on average, right? What does this mean is that this post tweet API is called these many times in every second, right? Second is my home timeline, right? Where basically I open Twitter, and then I can see all of the tweets by the people who I follow, right? and that API is called 3 lakh times or 300k times per second, right? Then can you guys tell me what is the problem in implementing this? Okay, so let's say I want to implement these two things together, right? Post tweet and home timeline. So can you tell me what are the two ways I can actually implement it? Guys? Yeah, just say look, guys. I don't want you to say the right answer. Otherwise, what will be the use of me? Right? Say anything. Say anything which comes to your mind.
We can like add something uh, for the users. Like we have to display certain tweets on the user's timeline, which are there.
But even
So
before going there, right? So just think about posting a tweet and getting tweets, right? Two things are there. I
Yeah,
post.
so
Yeah.
I do think that we can implement it if we're working with non-relational databases. So for any user, if we are having
We need to go for databases. Let's leave databases. There's a high level problem here, even before going to databases and all of those things. You know.
okay,
Yeah. So okay, I'll. This is the first case study, so I'll just try to tell you guys what I'm going for. So
Shubhankit,
yeah. Yes.
yeah, could you please elaborate the question? Like, actually, I'm not
Sure.
getting the question right correctly.
Sure. So Twitter has two operations: post tweet and home timeline. So the post tweet API है. So one post tweet API is there, and one home timeline API is there, right? One post tweet API is there. So whenever a user wants to tweet, right, they will simply call the post tweet API, right? And this will basically publish a new message to each of their followers. And this API, post tweet API, is called 4.6k times per second. This part is clear?
Sure. Yeah.
Yeah. Then there is your home timeline API. So this timeline API is nothing but the API which will be called to load all of their tweets whenever you first open Twitter, right? As the name mentions, it is home timeline. And this is called by 300 people, let's say. 300k requests per second, right? 300k people will call it. I'm saying 300k people will call it because per second there is a very less likely chance that one user will actually call it twice. So that is why I'm saying 300k people will call this API.
okay. So Shubhangi, is this the question related to scalability? You're saying that how we'll be scaling these many requests? That's what you're saying?
So there are two things that happen. Okay. So whenever I post a tweet, one way to solve is that as soon as I posted a tweet, I simply insert it into a global collection of tweets. I have a tweets table, let's say, and that tweets table will have things like my uh, I will have tweet text, my sender ID, and my follower ID. So basically, both ends of the tweet, who will receive it and who's getting it,
Yeah, right.
right? But do you actually want to store both? No, because who will receive it? A tweet posted by somebody will be received by multiple people, right? So in my tweets table, what I will have is just the tweet text and the guy who posted it, that guy's ID. This is clear?
Yeah, got it.
Yeah. So that is simply what a post. That is one way to solve this, right? So I have a simple table of tweets in which I have my tweet and I have the user ID of the guy who posted it. Another thing is, so now when a user will request their home timeline, how do you get all of the tweets, right? So there, yeah. Say.
So I think what you're saying is that we'll be adding that particular user with the tweet and the table, and uh, whichever user he's following, then for that particular user, we'll be checking whether there are any messages from the people he's following, right? From
Yes.
that table, we'll be getting the user.
Yes,
Okay.
yes. So what we end up doing is, so when a user requests their home timeline, right? Let's say I am a user, you know. So what, and you posted the tweet. So I will first see whenever I need to load the home timeline API, it will see the number of people who I am following, right? And then I will try to fetch all the tweets of the people who I am following. and I'll merge them.
Yeah, right.
Pretty straightforward, right? So I'll basically uh, like go to my following list, and I'll try to see all the tweets which I have posted, but I will see all of these tweets in this global collection of tweets in the main table. That is one way to solve it. We are going to get towards the main part. Don't worry, guys. Another way to solve it is that you maintain a cache for each user's home timeline. Okay, so I have my let's say I was the user. I had a home timeline. I have maintained a local cache, or let's say a cache at a server level as well, right, for every user. And then whenever a user posts a tweet, look up all the people who follow that user and insert the new tweet into each of their home timeline caches. So let's say now you post a tweet, right? As soon as you posted that tweet is updated into my cache, my local cache. And then I'm able to see it because I'm anyways fetching from the cache, correct? So whenever you're thinking of operations, you can either make the read expensive or you can make the write expensive, right? So let's go back. I know it might be confusing initially. So your post tweet is nothing. Yeah, go ahead.
Yeah. So my question is that if, for example, I am requesting for the home timeline, then I'll check for my followers or for the one who is posting for his followers. That I am confused.
No, if you're clicking home timeline, just naturally thing. Na? If you are going on home timeline, you will try to see the people who you are following, right?
Okay. And their tweets, if they are posted.
100 tweets, obviously, right? If I follow Elon Musk, I will basically see that, okay, whether I follow Elon Musk or not, and then I'll try to fetch Elon's tweet. That is the way to solve it, right?
Okay, this was the first, no? That you were
This
saying.
was the first one, correct? Absolutely correct. This was the first one. So again, let me reiterate. Post tweet is nothing but writing a tweet. Home timeline is nothing but reading a tweet. A write operation and a read operation. In most of the cases in the world, a read operation is always going to be more in terms of load than a write operation, right? My read operation, the load will always be more because people post less and watch more. Simple. And because my read operation is actually more, my write operation is less in number of quantity. What does it say? I will try to make my read operation less expensive, and I will try to make my write operation more expensive. Does this make sense to you guys?
Yeah, right.
Okay.
Yes, yes.
Yeah, pretty straightforward, right? Something which is less in quantity, you increase the price of it. Something which is more in quantity, you try to decrease the price of it. Same thing. So what is happening in this scenario, when I post a simple tweet, right? My write was anyways less in number, and posting is still pretty straightforward. I simply insert it into the table, right? So it is cheap. And my reading, which was anyways so much more in number, then I again go back to the main table and it becomes very expensive, right? Because my tweets table will be huge, right? And my number of users are also huge. So indexing on the number of users is also next to impossible, right? You index on a particular range or on a group of things. You cannot index on user ID. You're able to get that, guys?
Yeah.
Yeah.
Yes.
Yeah. So again, so basically this approach is obviously less good, right? Because my writing operation, which is anyways less in number, is less expensive, and my reading operation, which is anyways high in number, is more expensive, right? And this is the design which actually Twitter followed, by the way, guys. So it's not like I'm cooking something up. So the first version of Twitter was actually using this approach, right? Which is not feasible. So again, like any trade-off thing, so they realize that, okay, why do I not make the write more expensive and the reads cheaper? How do I do that? My write is now expensive because now it actually needs to update cache, right? So let's say if Nishant posted his tweet, right, and 10 people follow Nishant, so that tweet needs to be updated into the cache of 10 other people, correct?
Yeah, right.
Yeah. So that way, your write has become
Yes.
more expensive now. because it is not just inserting into a simple table, it is actually affecting 10 caches of 10 people, right? But my read is now easy because read is just simply going through the cache. Read is just reading up from the cache, and cache is at a user level. Everybody has a local cache, so I don't need to think about that. So this way, my expensive operation has become the guy which is less in quantity, and my cheap operation has become the guy which is more in quantity. So that way, I've saved costs here. But again, it's not that simple, obviously, because when I say I write a post and it'll update, let's say, caches of 10 people, right? Then what happens when I have 10 million followers? Right? Then I'll be basically updating caches of 10 million people. So this is a classic example of fan out problem. Okay. So user posts a tweet, right? All tweets, and you deliver tweet to each follower. So these are tweets for recipient 1, recipient 2. These are local caches. If you have 31 million followers allowed per user, this is because 31 million because int max, right? I'm guessing int max. I'm just not thinking right now. So int max. So I will actually have to update this, right? So basically what ends up happening is my 4.6K writes per second actually turn into 345K writes per second. Why? Because on average, one user will be at least writing to 50 or 100 users, right? So if I post a tweet, it will get reflected in 100 caches on average. So that is why this 4.6K writes per second becomes 345K writes per second. But my read now it is more than the reads. Then again it is wrong, correct? Is this clear to you guys?
Yeah.
I know I'm saying a lot of things in the air, but I'm
Yeah, it's
Yeah.
clear.
okay.
Yeah,
Cool.
all the tweets would be stored in the cache, right?
So for user level cache. So again, basically my
Yeah.
4.6K writes per second is now 345K writes per second because I'm fanning out, because I am going to update it in every, I'm writing one tweet, right, is actually getting updated, is actually getting written into 100 caches on average, right? And that is why this is a
Yeah,
simple
got
fan
it.
out problem. So how do they solve this? Pretty straightforward, nothing genius, like all of us could have thought about it. That what you do is, again, it is written that on average a tweet is delivered to 75 followers, and that is why it becomes 345K writes per second. But this average hides the fact the number of followers per user varies widely, right? And then there are something called celebrities. This means that a single result may result in over 30 million writes to home timelines, which is stupid, right? So what you do here is you create a separate table for celebrities and their tweets. And then for the user, I will try to see the number of celebrities which I maintain. For every user, I'll try to see the number of celebrities they follow. First, I'll try to fetch their tweets separately in the home timeline, so that I don't need to update it to the cache. So whenever a celebrity posts, I keep it in a separate celebrity tweet table, right? I do not keep it. I also keep it in the global table, but I do not use that to update it to multiple caches, right? So whenever a celebrity posts, I fetch it separately every single time for every user. Is that
Okay,
clear?
means that tweet won't be in our local cache, right? If we are following that celebrity.
Correct. Yeah. So basically, let's say now I try to call home timeline API. So what the home timeline API will have, the first thing it will try to do is it will say get celebrity tweets, right? So inside that home timeline, it will have multiple functions. I will say get celebrity tweets, that is separate function. And then second thing can be get local cache tweets. And then my third thing will be appending celebrity tweets and local cache tweets together and then serving it to me. So that is how you serve it, by solving the fan out problem. Again, just to give you a brief flavor of what we are going for, right? Everything will be discussed in extreme detail. But again, we'll revisit this in chapter 12. But I think this is more than enough for you guys to understand why sometimes reads versus writes matter, right?
Yeah.
Any doubts you can you guys can ask
Got
me.
it.
Okay. Fine. Now describing performance. Once you have described the load on a system, you can investigate what happens when the load increases. You can look at it in two ways. When you increase the load parameter and keep the system resources unchanged, how is the performance of your system affected, right? This is the classic case, right? Your system did not scale, but I got peak traffic. What part started to fail, right? This is what this thing is saying. Second thing is, when you increase the load parameter, how much do you need to increase the resources if you want to keep performance unchanged, right? What is the level to which we should scale up if my load increases? So you need both, right? Until unless I know what services will fail when my load is going to increase, I will not be able to increase the load in those particular services, right? That is why you first need to figure out what services in which it will fail. Second thing you'll figure out is that, okay, I know this service is going to fail, then I'll do something called load testing. I'll try to see if 7x of my usual traffic, uh, it is going to fail or not. Because 5x is my peak traffic. When I say x, it means my average traffic. 5x is peak traffic. 7x is the traffic for which we test, right? We are trying to be a little safe here. If I do not want reliability, I can only test for, let's say, 5x, which is exactly the same as peak traffic. But in a lot of production incidents, what ends up happening is you go just a little overboard peak traffic so that you're a bit safe if you're unable to anticipate your peak traffic. Fine. Both questions require performance numbers, and now basically it comes to managing performance, or how do you measure performance of a system, right? We understood how to measure load, and that defines scalability. How to measure performance requires you to check about performance metrics. One great performance metrics is throughput. I think with Nishant we have discussed this too much. Throughput is the number of records we can process per second, the number of orders which we can process per second, or the total time it takes to run a job on a data of certain size, right? This is for you, right? This can help you there. So you need to check the throughput of your pipelines sometimes. In online systems, what's usually more important is the service's response time, right? I think Amazon P99 is damn famous that they try to make sure that their API's response time is on average giving you the best response time. I will elaborate more on that. Just wait a few seconds, right? But a response time is a very good way to see that, okay, the latency of your API is a very good way to see that, okay, my system is performant. It is able to do things fast. Again, one thing which everybody ends up confusing is latency and response time. Not the same things. Response time is what the client sees, right? Actual time to process the request. Service time. It includes network delays and queuing delays. Latency is a duration what a request is, data request is waiting to be handled, during which it is latent, awaiting service. So again, response time is pretty straightforward. So I as soon as I click the button, right, the next time I am able to, let's say, go to any other usable action, that is the entire time, which is the response time, right? Basically the actual time taken to process the request. It has network delays, queuing delays. Latency is the duration that a request is waiting to be handled, right? So basically the time in which your API is starting to get executed and the time at which the client sent the request. The difference between those times is what defines latency, right? How latent your system is. So a very good example of this is, let's say I have a messaging queue, right? My order on average will take at least 1 minute to process. Why? Because I have a throughput which only allows, let's say, one order per minute, right? So that 1 minute will be latency because it takes 1 minute of time for my order to be processed. After that, my order might take 5 minutes to process. And if I add that 1 minute plus those 5 minutes, that will together form the response time.
Okay. Yeah. Got it.
Okay, cool. Even if you only make the same request over and over again, you'll get a slightly different response on every try, right? Very common. Your request, Vyom, you would have seen, right? Every single time you tried calling the API, it was different, right? It was a few milliseconds off. And for that, like all things in life, you require probability, right? You require a distribution. And what you need to basically see is the percentile, right? So the percentile is where basically, if you guys will see in any production environment, there are things called P99, P95, P50, right? A lot of the people who are as senior as me or even more, nobody knows what P99 is. But what it actually means is it's a very simple thing. 99 percentile, right? That only 1 percentile of let's say my requests are going to take more than X seconds. let's say if I say my P99 is 1 millisecond, right? It means 99 percentile will of my requests will get executed in less than 1 millisecond, right? Just the 1% will go above that. And as a company or as any technical system, it's a job to reach till P99. Most companies suffice till P95, and today most startups are okay with P50, right? But like P95 is a good spot. P99 is when you're customer obsessed, as Amazon says, and then you try to achieve P99, right? It's common to see the average response time of a service reported. Yeah. So most of the times when say I am a broker, right? I want to see tell my users that okay, this is the response time. My P95 will be higher, right? Because I am tracking 95 percentile here. I'm trying to see okay, 95% of my requests should be less than the second. So obviously my P95 will be higher in time. My P50 will be extremely less, which means that 50% will take less than whatever time you say, let's say 1 millisecond, and 50% will take more than 1 millisecond. So it is beneficial if I am provider of an API, I will just mention my P average, right? But if I want to be performant, I should aim for P95. And whenever you're trying to read API documentations, you can see that okay, is this guy actually mentioning P95 or P50? And that is how you compare APIs between different brokers. Like one way to compare. Is this
Shubhankar, can you repeat this last part?
okay? So let's say I have two
Average one.
brokers, right? Average one, yeah. So again, percentile, right? So let's say I have 10 API calls, right? 10 API calls. 5 of them took 2 milliseconds, right? And 5 of them took 8 milliseconds, right? So what will be the average time?
Sorry, 5.
5, exactly, right? 5 millisecond will be the average time. So the guy will say that okay, my APIs actually take less than 2 milliseconds at P50, right? Or less than 5 milliseconds at P50, right? Because 50% of my requests are actually taking less than that time, which is 5 milliseconds. And one guy was saying that my APIs take, let's say, 6 milliseconds, right? And that guy was saying that that is my P99, not my P50. Basically, 99% times my API takes 6 milliseconds or less, right? So I would prefer a P99 of 6 milliseconds than a P50 of 5 milliseconds, right?
Yeah.
Yeah, so that is how you compare, right? When you start choosing between separate brokers, this is for everybody. So you try to see, okay, whether this guy is actually mentioning my P50, P99, P95, all of those things. Or you can call it anything. I call it P90, P99 because that is how it is mentioned in a lot of softwares. In Grafana and Prometheus, it is mentioned like that, and that is I'm saying that. Again, it is better to use percentiles. So a mean is nothing but a mean, right? It is not an ordering. A percentile or a P50 is a median, not a mean. Right? Simple statistics, you guys can revise it. Again, same thing. Right? Yeah, see, abbreviated P95, 99, P999. P999 is what Amazon goes for sometimes, 99.99, 1.9, right? High percentiles of response times are also known as tail latencies are important because they directly affect users' experience of the service. For example, Amazon describes response time requirements for internal services in terms of 99.9th percentile, even though it only affects 1 in 1,000 requests. This is because the customers with the slowest requests are often those who have the most data on their accounts because they have made the most purchases, right? This is a very good thing to see, right? I can say that okay, only 1 in 1,000 is actually failing, but that one guy was the guy who made so many orders or had so many things in their cart. So I actually need to solve for my peak customer. If I'm not solving for them, then what's the point, right? So that is also, you should not just think about P99. You also need to see that okay, at here I need to go for P99.9 because the guy with the maximum load or the guy which is actually profiting me the most is the guy who's getting affected, right? And that is why you go for something called P99.9 also sometimes. Yeah, and certain times optimizing the 99.99 was deemed too expensive even for Amazon, right? And then they decided that they'll not go for this. They only go till P99.9, which is more than good for them. Again, for all of this, you have service level agreements, SLAs. These are contracts that define expected performance. So let's say if you're in big tech and you write an API, you will basically write an SLA document that says that, okay, I am going to write this API, and you will write an API contract that any tenant of this API should basically expect a response time like this, right? And let's say if I am a user, right? If I am the one who's demanding a service, so I will again say that I want a median response time of less than 200 milliseconds. Okay. If you're not able to do that, please change something in your API. I don't care. Right. So SLAs define everything. SLAs is nothing but a contract. Sorry. Yeah, I was talking about latency and response time, right? Queuing delays often account for a large part of the response time at high percentiles, right? As I said, multiple orders, huge queue, your queuing delay is the one which is going to actually trouble the user the most. As a server can only process a small number of things in parallel, limited for example by its number of CPU cores, right? That is why I keep on focusing on the CPU threads and the number of cores, right? Until unless your CPU is high, what is the point of if until unless your CPU cores are not high, what is the point of making 50 threads, right? It should be directly tied to your CPU cores. So, and that is why it only takes a small number of slow requests to hold up the processing of subsequent requests. Because my CPU does not have, let's say, more than 100 cores, for example. A huge set, but not more than 100 cores, right? And I only have 100 users, although I am serving 10 lakh users, right? If those 100 users actually block everything, right, then I'm stuck, right? Then I don't know how to process this. And this is called a head of line blocking. Basically, the head of the line is actually blocking everything, like most things in life. So even if those subsequent requests are fast to process on the server, the client will see an overall slow response time due to the time waiting for the prior request to complete. Right? This is basically increasing the latency and the response time, because response time also has a latency, but it is not increasing the processing time. So due to this effect, it is important to measure response time on the client side. Yeah, something which we actually end up missing. Let's say you're working on a startup, you will only measure, let's say, the latency and try to see the processing time. We need to see the response time, right? The processing time does not matter. It is going to be in most of the cases, it is going to be fast. The thing which is of use is response time. This we do not measure right now, even at Invsto. We only measure processing time because we are not at that stage yet. But fine. So when generating load artificially in order to test the scalability of the system, the load generating client needs to keep sending requests independently of the response time. If the client waits for the previous request to complete before sending the next one, the behavior has the effect of artificially keeping the queues shorter in the test than they would be in reality, which skews the measurements, right? So if the client waits for the previous request to complete, right? So I'm doing load testing, right? In my load testing, I only send a request until unless my current request is completed, right? So basically, then that is messing up things, right? Because my queue is going to be empty then my queue will not be long. Ideally, it should completely bombard it with requests so that my queue is able to actually emulate a real-time load, and so that the line will be longer. So this is what it is trying to say, that keeping the queues artificially shorter in tests than they would be in reality, right? Because I'm not sending it enough requests because I'm waiting for the previous request to get completed. So that is why you implement load testing carefully. Yeah, percentiles in practice, again, there are things called tail latency amplification and everything. I will get into more detail, but I think this will require, let's say, a little bit more knowledge. So let's wait on this for some time. And let's go for approaches for coping with load, right? But even before going there, I think we only have, we are almost there, 2 pages more, right? Even before going there, guys, any questions, anything?
No, not for now.
Okay. I'll actually just go get water. I'm speaking for too long. I'm not used to speaking for this long. So I'll just go get water and come back.
Yeah, sure.
Hey guys, I'm back. I actually did not think it'll take this time to finish the chapter. But yeah, fine. Approaches for coping with load. Okay. Now that we have discussed the parameters for describing load and metrics for measuring performance, we can start discussing scalability in earnest, right? Basically, you're saying that now we know how to define load, we know how to define performance metrics. Now let's go and say that, okay, when we have good performance, even when our load is increased, right? Because if I know when my performance is good, when my load is increased, what am I actually testing? Scalability, correct? That was the point. That was the reason why I was checking for performance and load both to test for scalability. An architecture that is appropriate for one level of load is unlikely to cope with 10 times that load. Pretty straightforward. If you're working on a fast growing service, it is therefore likely that you will need to rethink your architecture on every order of magnitude load increase, right? Perhaps often talk of a dichotomy between scaling up and scaling out. Scaling up is going to a powerful machine, vertical scaling, horizontal scaling is again keeping multiple machines, right? So, like say on AWS, right? Whether you go for a stronger CPU or do you keep multiple CPU with less cores? Depends on the kind of things you want. If you want, let's say, independent implementations, I will go for horizontal scaling. If I want everything to be a monolith, I will go for a vertical scaling kind of setup, but again, requires more context. Distributing load across multiple machines is also known as shared nothing architecture, right? Again, like I said, if you're independent, you're sharing nothing, right? Hence, it is called shared nothing architecture, which is horizontal scaling. A system that can run on a single machine, often simpler, but high-end machines can become very expensive, obviously, right? So two i5s are cheaper than one i9, right? That is how I will describe it. So if I can do well with two i5s, I will go for that. A very good example of this is if I have multiple users on a website. Ideally, the website does not take time. I just need multiple parallel cores. So I'll go for two i5s, right? But if I'm making an ML model, right? The ML model needs to be entirely loaded in memory, and then it needs to do all of the processing. Then I'll go for a stronger machine, right? Let's say an M3 Max chip, which is SoC and can use a lot of CPU details. I can go into CPUs a lot more, but I'll stop. In reality, good architectures usually involve a pragmatic mixture of approaches. For example, using several fairly powerful machines can still be simpler and cheaper than a large number of small virtual machines. Some systems are elastic, meaning that they can automatically add computing resources when they detect a load increase. Basically, what it is trying to say is auto scaling, right? In AWS, you have a way to auto scale. Basically, if you see that more load is getting increased, you automatically add another instance. When some you need to scale manually. I think this is the time when Jenkins was a building software, and then you would actually scale things manually on your box, right? You would, let's say, fire up another instance, you will switch on the box, and then you will deploy things. An elastic system can be useful if your load is highly unpredictable, right? And a manually scaled system is simpler and have fewer operational surprises, right? So let's say if you had an outage on your end, right? And for some reason, some of your service was bombarding one of your servers, right? But it was not because of peak user thing, but it was just your own internal error. Then it would unnecessarily increase the compute cost, right? Because you were not anticipating it, but your system is highly volatile. As soon as load increases, it will auto scale. So again, you need to realize that okay, I need to auto scale only if it is highly unpredictable, Also, I need to put certain error mechanisms in check so that I don't end up auto scaling for no reason and increasing my compute cost exponentially, right? And again, that sometimes that is why you prefer manually scaled systems, because you know that my system is not going to scale to that level. Like a excerpt can be, when do you know that my system is not going to scale till that level? A very good example of this is trading, right? The number of daily active traders in India is 30 lakhs, let's say for now, right? It is never going to be more than 30 lakhs, right? Because the users on our platform will always be less than the overall number of traders on the board, correct? So that is one way you can say that, okay, it is never going to increase that load. So I do manual scaling there. Fine. While distributing stateless services across multiple machines is fairly straightforward, taking stateful data systems from a single node to a distributed setup can introduce a lot of additional complexity. Stateless, stateful are things where you try to maintain, let's say, separate states. A very good example of a stateful system is a database, right? If I have a database which is split across multiple nodes, then how do I keep it consistent, right? If I have a simple cache or a CDN, I can obviously split it across multiple things because that is not my primary source of truth. If I have a primary source of truth, right, I cannot, let's say, deduct money from one of my SQL servers in the north and then also deduct money in one of the SQL servers in my south. My SQL server in my north should actually tell me that my SQL server in south, that whenever it is updated, so that my SQL server in south is also able to have the latest information, right? So a stateful system is actually much more complex to be in a distributed setup because you actually require all of those distributed nodes to talk to each other as well. Yeah, for this reason, common wisdom until recently was to keep your database on a single node, scale up, until scaling costs or high availability requirements forced you to make it distributed. That is why SQL is amazing, right? SQL is able to scale up on a single machine in a great way. And but again, after some point, you will not be able to scale up and you will be required to have multiple servers. As the tools and abstractions for distributed systems get better, this common wisdom may change. At least for some kind of applications, it is conceivable that distributed data systems will become the default in future, even for use cases that don't handle large volumes of data traffic. Over the course of the rest of this book, we'll cover many topics, right? The architecture of systems that operate at a large scale is usually highly specific to the application. Obviously, there's no one-size-fits-all architecture. The problem may be the volume of reads, the volume of writes, the volume of data to store, access patterns, all of those things. Let's take an example. I think a system that is designed to handle 100K requests per second, each 1 KB in size, looks very different from a system that is designed for 3 requests per second, each 2 GB in size, right? Very good example of this is DALI, right? DALI might be in less requests per second, right? But all of those requests will be huge in compute compared to Google. Can be able to handle more requests where the request can be less in size, not 1 KB, but just giving you an example. An architecture that scales well for particular applications built around assumptions of which operations will be common, right? You make certain assumptions in an early stage startup. It's usually more important to be able to iterate quickly, and than it is to scale, right? That is why we don't talk about scaling. We need to build the product first. Maintainability, the thing which you guys absolutely work on. Like majority of the cost of software is not in its initial development, but in its ongoing maintenance, fixing bugs, right? We are like feature development obviously takes less time. Solving bugs will take your life. So yeah. Yet unfortunately, many people working on software systems dislike maintenance of so-called legacy systems. Like I have worked on Windows, guys. Trust me, there's documentation from 1986 which I've read. So not the best systems to work on, because it involves fixing other people's mistakes. Like people who made changes in them, their kids have retired, so it's sometimes that old, and that is why it is absolutely irritating to maintain code, especially legacy code. However, we should design and we can design software in a way that it can minimize pain during maintenance, right? Thus avoid creating legacy software ourselves. Very good thing is that if you actually not end up dealing your backlog, right? Most of the times what ends up happening is we realize, okay, this deadline is coming, and then I can delay this feature for this long, right? Even you would have seen me delaying a lot of features personally. It is predominantly because to match timelines, right? So I will postpone certain thing and then I never pick it up, right? And then again, it again creates a legacy kind of software, and then I again have to reiterate it. So ideally, we should solve it as soon as it comes, instead of actually delaying it. But again, it's a trade-off, right? Certain times you will focus on timelines, certain times you will focus on not creating legacy, right? So again, in terms of maintainability, three things: operability, making it easy for operations team to keep the system running smoothly, right? This requires your on-call handbook and all of those things, right? Basically, when my EC2 is down, when my data is down, I have specific commands for it to rerun things. Simplicity, the code is written in a simple way, it is well commented, all of those things which you have studied in college probably. If not, then again, it's nothing but writing neat code, right? That is how you start naming variables correctly, all of those things. Evolvability and extensible design, right? Uh, this is the thing which you'll be focusing on the most when you become a senior engineer, that whenever you have extensible design, it makes it easy for me to make changes. Take Zerodha, for example. So when Zerodha actually faced RBI problems, so RBI is known to change its regulations very quickly, right? So as soon as those regulations got changed quickly, Zerodha was actually able to make all of those changes pretty quickly because most of the services were plug and play, right? On the other hand, if I'm some other broker, I will not name any other broker, but if I'm some other broker, I might not have an extensible design, right? And then I won't be able to, let's say, comply to regulations in a way in which Zerodha does. Again, just an example, not quoting any company for anything. Operability, making life easy for operations. Good operations can often work around the limitations of bad software, but good software cannot run reliably with bad operations, right? So basically, if you are unable to monitor the health of the system, there's no health check, there is no way to track failures, there's no way to track errors, there's no telemetry, right? There's no security patch, right? Then your system can never run, right? If my system does not even have a simple security patch, then nobody will use my system, right? Even if I have a beautiful trading platform, nobody will use it because it's unreliable and again not easy to operate. So I think sometimes you need to focus on operability a lot more. Another thing is anticipating future problems and solving them before they occur, right? Capacity planning. So again, sale is coming, peak traffic, you go beforehand to increase the scale. Establishing good practices, all of those handbook things which I constantly say, preserving organization's knowledge, basically documentation, defining processes that makes operations predictable, again covered in handbook, right? Maintaining the security of the system, again, basically classic software engineering. Have good documentation, have good testing, have neater code, simple things, right? Good operability means making routines easy, providing visibility into the runtime behavior and internal systems with good monitoring, right? This thing we actually is covered by telemetry. We do not do telemetry a lot, right? We for that Grafana will be required for all of the data metrics and all of those things, right? We need to see, okay, what is the latency on average for all of the other APIs, not just for one API and not just while testing, right? So we need good visibility into the runtime behavior, right? And internals of the system, basically things like how many cores get engaged, when you scale, all of those things. Basically, it's saying one thing: you need to understand everything to be good at it. You need to document everything to be good at it. And you need to have proper on-call handbooks. So let's say when things fail, there are specific commands which can run with ease so that you can roll back easily, right? Let's say there are 10 people in the team, 9 are off, one guy is on, but he does not know how to roll back. So that should be there in some documentation, right? Exhibiting predictable behavior, minimizing surprises. If one guy saw an error, they should ideally write it down somewhere and say, okay, this is the solve to fix this error. So that next time, if anybody faces this error, and if that person has left the company, there is somebody who can solve the error. Simplicity, managing complexities. Small software projects can have delightfully simple and expressive code, but as projects get larger, they often get very complex and difficult to understand. A software project mired in complexity is sometimes described as a big ball of mud. Absolutely. Right? It is nothing but pure mud because PG-13. There are various possible symptoms of complexity: explosion of the state space, um, tight coupling of modules, right? A lot of times, let's say, if you have orders, right? Are a very common thing. I can have 3 states, 5 states. If I have 25 states, it is absolutely pointless, right? Uh, Another thing, what explosion of the state space can mean is, let's say, states of the databases, right? I do not need to have so many states that uh, I'm constantly changing state at every single thing, right? So another thing, let me explain it to you in a better way. Hmm. So if I have 3 states, I can easily convert them, right? But and that way my load will not increase because my interaction times between distributed nodes will actually decrease. But if I have 25 states, every single time there's a write in my DB, I will end up, let's say, updating the state of the DB, right? Now this is updated DB. This is updated 2 DB, updated 3 DB, updated 4 DB. You know, now I have 4 states. Now which one will be best? So to solve all of this, I will need to form a consensus server, which will define the quorum of the number of servers which have the same state, and then you basically propagate it again. So basically, the minimum amount of states you have, the better it is, right? But you still need a basic number of states for your application to function. Your tight coupling of modules, right? A very good example of this is how Atom is written. Most of the times, whenever there's some problem, let's say in let's say OMS, we blame it on Atom. Atom blames it on OMS, or strategy engine blames it on Atom again. So Atom is something which is very tightly coupled, right? Ideally, it should not be. Tangled dependencies is another thing, right? So let's say if my service is always going to use Atom, right, and that is using a certain dependency, and I am also using the same dependency, and both of them are separate versions, right, and the same machine ideally will not maintain both the versions. We can, but sometimes it will create inconsistencies, right? And that is why you shouldn't have tangled dependencies. You can't have inconsistent naming. You can't call orders transactions, right, for example. All of these help in solving performance problems and all of those other things. Again, while complexity makes maintenance hard, budgets and schedules are often overrun, right? In complex software, there is also great risk of introducing bugs when making a change. Obviously, if something is complex, you will have a lot of cascading faults. Making a system simpler does not simply mean reducing its functionality, right? It can also mean removing accidental complexity. If it is not inherent in the problem that software solves, but arises only from implementation, right? A good example can be, let's say, if I'm using Python, right? And Python might not have, let's say, a lot of command over operating system, right? So to solve that, I will use something called C Python, right? And then Python will basically call C Python. C Python will write C code. Then that C code is going to, let's say, act on my OS, right? So it is the implementation which is causing the problem, because ideally this time should not have been taken if I would have just written the code in C++, right? So that is how you remove accidental complexity. Again, might be a bad example. I can come up with better ones, but again, I have not read this since a long time, so I'm just speaking things right now. One of the best tools we have for removing accidental complexity is abstraction. Right? A good abstraction can hide a great deal of implementation detail behind a clean, simple to understand facade. A good abstraction can also be used for a wide range of different applications. Right? Uh, Again, so what this basically means is that, let's say if I have a lot of implementation, but Atom is a library, right? If Atom has, let's say, less amount of functions which are exposed, right? Right now, Atom, let's say, exposes everything. But if Atom, the library which we use, if it has less amount of functions exposed, then it will be easier for me as a user of Atom, right? I only know that, okay, there are 10 operations. Other than this, nothing can happen. I cannot access other things. How? I have declared all of my other methods private. One very simple example of it, right? Because in my actual function, I will, let's say, have a function called get calls, right? And in Atom also, let's assume I have the same function, and that function was not private. Then I might end up implementing the Atom's get call instead of my get call, right? one place where again implementation is introducing complexity and we need to change it. Again, for example, high-level programming abstractions that hide machine CPU code, CPU registers calls, right? SQL is an abstraction that hides complex on-disk and memory DS. All of these things are there. Solvability, making change easy. It's extremely unlikely that a system's requirement will remain unchanged forever. They are much more likely to be in a constant flux. You learn new facts, previously unanticipated use cases emerge, your priorities change, your startup may fail. Who knows, right? So all of those things, your system should be smart enough, right? In terms of organizational process, agile, I think I have discussed about agile too much. Scrum, story points, all of those things, right? And there are separate kind of, let's say, techniques which you can employ, right? Scrum and agile is one way, right? Another way is to do TDD. So TDD is very ideal, and I am actually have a controversial opinion about TDD. But so how do you do TDD, right? So first thing which you do before writing the code is you first write test cases, right? And then you start writing code to solve those test cases. But you write the test files first. That is how you do TDD in an ideal environment. You first define the test plan, then you start writing test cases, then you start implementing things which will solve all the test cases one by one. And finally, all of your test cases are solved, it means your function has been implemented. But because of speed constraints, time constraints, money constraints, TDD sometimes becomes harder to implement. Yeah, again, most discussions of these agile techniques focus on a fairly small local scale. In this book, we search for ways of increasing agility on the level of a larger data system, perhaps consisting of several different applications or services with different characteristics. Like I think later on they describe how would you refactor Twitter's architecture for assembling home timelines, right? That is one way in which you can think about separate techniques which we can use along with agile techniques, right? But since this is an important idea, we will use a different word to refer to agility on a data system, evolvability. Like, did you guys understand this part? Even I was not very good at explaining this part. Let me retry, right? It is extremely unlikely that a system, basically, you are able to evolve, right? But it is not about being agile, right? It is also about looking too much into the future, right? Agile is a very local thing, right? Agile is okay, my next week, next to next week, or let's say my next sprint or my third month sprint, right? Max to max third sprint. My evolvability will look something beyond the years, right? So it's a time frame thing. Now let's talk about summary. An application has to meet various requirements. There's something called functional requirements, right? What it should do, allowing data to be stored, what all APIs should work on. Then there are NFRs, which are non-functional requirements, which is security, compliance, scalability, compatibility, maintainability, right? Performance is a very good part of NFR, right? How fast my application should be is NFR. FR should be whether it is able to do things or not, which I want. Reliability means, again, making things work correctly. Scalability means making them like performance, making their performance actually constant irrespective of the amount of load. And maintainability, let's say, has things like if multiple people work on it, I have, let's say, good abstractions, good operability, good visibility into systems health, so that I can maintain code. Again, no easy fix for making applications reliable, scalable, or maintainable. Certain patterns and techniques that keep reappearing in different kind of applications. And again, we'll look into the book later. Yeah, and we are done with chapter 1, guys. I think this is the most I've spoken in a long time. But yeah, let me know, guys, if you have any doubts. I will stop the recording.